Okay, so let's take a look. Again, the stoichiometry problem. It's pretty much the one we did in that lab. We want to follow our steps. So we want to balance equation, which obviously here we do have. We want to take whatever they gave us and convert it into moles, which is this guy. We are given STP, so remember the STP does stand for actual value, so that's 273.15 for the temperature. That's a pressure of 1 atmosphere is basically our STP. And ultimately, we want to find the volume here of our hydrogen gas. So we can think about our PV equals nRT, and we have temperature. We're looking for the volume. We do have pressure. We always have R. So the one thing we're really missing in terms of the hydrogen gas is the moles, and that's what we're going to use basically the stoichiometry part to get to the moles so that we can get to the volume. So we do need to start here actually with the magnesium because that's the only piece of information we have. We're going to use stoichiometry to go from magnesium to moles of hydrogen, and that's going to allow us to ultimately solve for what we're looking for here. And again, we always have R, which is our 0.08206 liters, atmosphere, Kelvin, and mole. So we'll start with kind of normal step 2, which is convert into moles. So that's 5 grams of magnesium. Going to use the molar mass of magnesium from the periodic table, 2431 grams per mole of magnesium. Remember that I don't really want moles of magnesium. I do want moles of hydrogen, and it is a 1-to-1 relationship. So when we look at that, we could see the equation: 1 mole of magnesium gives us 1 mole of hydrogen. So I could get an answer at this point, or I could just continue on with the calculation, which is what I'm going to do. I have moles basically of magnesium on top, which means I do need moles of magnesium on the bottom to cancel, and moles of hydrogen on the top, and that's going to cancel. That's basically our third step, which is our stoichiometry part of the calculation. So that's going to get us here 5 divided by 24.31. And we'll go 0.2057 moles of hydrogen. So we now have the moles of hydrogen that we're missing using our stoichiometry. So really our last step here is we're going to use the ideal gas law. And in this case, we're going to solve for V, which means we're going to send P to the other side and divide by it. And V would equal nRT divided by P. Putting in our numbers here, 0.2057 mole, our R value, our temperature, which is STP, and our pressure, which is also from the STP part. The atmospheres will cancel, the moles will cancel, and the Kelvin will cancel. It's actually just going to leave us liters as our answer. And in that case, looks like we will end up with about 4.61 liters. First off, any question on that calculation? Now, could I have solved this another way? The answer is yes. And it's one of these situations where, because we are at that STP conditions, we know that at STP, 1 mole of any gas will basically equal 22.414 liters. So without using the ideal gas law here, we could have actually just picked up with our moles and use that conversion because it is at STP, so we're allowed to use that conversion if we wanted to. So we could have just took our 0.2057 moles of hydrogen, did our 1 mole of hydrogen in this case would equal 22.414 liters. The moles of hydrogen will cancel. And again, we should pretty much get the exact same number there, 4.61 liters. So in this case, you do have that option to use that conversion factor. You don't have to, like you can see, and just use the ideal gas law. So as we talked about, remember, you can always use the ideal gas law regardless of the situation, if it's STP or non-STP conditions. But once again, you can only use that bottom conversion if it is at STP conditions. So if it's not STP conditions, you cannot use the bottom one. Any questions on either of those there? All right, so let's take a look at one last little sort of stoichiometry problem here and sort of see what we got going on. All right, so we got calcium carbonate reacts with hydrochloric acid to produce carbon dioxide gas. If we take 35.3 grams of calcium carbonate and react it with 21.9, it's kind of like 200, I suppose, 21.9 grams of HCl, we're looking for how many liters of carbon dioxide will be produced at 745 millimeters of mercury and 23 degrees Celsius. So this is definitely a stoichiometry problem. In this case, we do not have an actual equation. So definitely we have everything in words. So we need to write our equation. So let's go with that. That's calcium carbonate. Calcium is +2, carbonate is -2. So again, we want to make sure we start with the right formulas here. And we're going to react it with hydrochloric acid, which is HCl, to produce carbon dioxide gas, which is CO2. And in this case, we do want to actually figure out how we get to CO2. So let's talk about really how we get there. There's some other stuff. If you're not sure, this is a double displacement reaction. So that's a positive, negative. That's a positive, negative. So these guys are going to switch partners. And when they do so, they will make calcium chloride. Again, calcium +2, chloride -1. So you do need two of them there. And really, when the hydrogen goes over there with the carbonate, you're going to make carbonic acid, which is this guy. This carbonic acid will very quickly decompose into H2O and CO2. So that is where basically our CO2 comes from. It's going to actually come from the decomposition of this guy. It's going to decompose to H2O, like I said there, and CO2. So that gives us really, since we're looking for the CO2 gas here, we are looking for that guy. So we'll leave that version of it in there so we could actually see it here, which is our CO2 gas. We'll get a little bit of that and a little bit of this, a little bit of that, and a little bit of that, probably. Now, in this particular case, we do need to balance it. So I think we need a 2 there. And at that point, I think we may be balanced. So we got 2 hydrogens, we got 2 Cls, 1 calcium on each side, 1 carbon on each side, and 3 oxygens on each side. So we are balanced in this case. First off, any questions on that there? So what's going to happen in this case is we are taking 35.3 grams of calcium carbonate. We're going to react it with 21.9 grams of HCl, and ultimately we're looking for the volume here of CO2. So since we're looking for the volume of this gas, we obviously have a pressure that's 745 millimeters of mercury, and we have a temperature that's 23 degrees Celsius. So once again, if we think about our ideal gas law, our PV equals nRT, we do have a temperature, we do have a pressure, we are looking for a volume, we always have R. So once again here, we will need to use stoichiometry to figure out the moles of the CO2, as that is our sort of missing piece there. Now, this is also a little bit different than the previous one that we did, which is, if I look at this, I have grams of this reactant, and I have grams of this reactant, which means for both of these guys, we could definitely get moles. And if you remember, that means that this is going to actually be a limiting reagent problem. So we do have to actually figure out the limiting reagent here because we have basically moles of each of those starting guys. So we don't know, which one's the excess and which one is the limiting. So remember that in sort of this type of stoichiometry with gases, you could still have a limiting reagent situation occurring. So I'm just going to steal some of the room up here to write. So we're going to follow our normal steps, which is we do want to convert what they gave us into moles. So we'll take our 35.3 grams of calcium carbonate. We'll go to the periodic table and calculate the molar mass of calcium carbonate. So that is 4008 for the calcium, plus 1201 for the carbon, and 3 times 16 for the oxygen. That's going to give us 100.1 grams per mole of calcium carbonate, again from the periodic table. And that will get us 0.3526 moles of calcium carbonate. We'll do the same thing for our other reactant, which is 21.9 grams of HCl. We'll go to the periodic table, get our molar mass of HCl, which is 1.008 for the hydrogen, 3545 for the chlorine, 3646 grams per mole of HCl. Again, from the periodic table there. So 21.9 divided by 3646 going to give us 0.600, and we'll call it 7 moles of HCl. Remember that these are really our starting amounts, right, of each of these guys. So as we talked about, we do need to do a little calculation to figure out how much of one reactant we need to use up the other and see if we have enough to determine if it's a limiting reagent or not. Or again, you can do 2 separate calculations to the end and figure it out whichever way you want to do it. So I'm going to take all of my calcium carbonate here and I want to use it up. So going to the equation, I can find the mole-to-mole relationship between my calcium carbonate and my HCl. It is a 1-to-2 relationship. So 1 mole calcium carbonate on the bottom gives me 2 moles of HCl. And that means that I would need 0.7052 moles of HCl is needed. So in this particular case, I want to compare that to how many moles of HCl I'm starting with, and I could see that I do not have enough. And because I do not have enough, that means in this case, actually my HCl will be my limiting reagent, and my calcium carbonate will be my excess reagent. Any questions on that there? Okay, so now that I know that it's my HCl, that's my limiting reagent, I want to continue on with my HCl starting moles. Again, I want to use my starting moles of it. I'm going to now do my mole-to-mole relationship between HCl and my CO2. So 2 moles of HCl from the equation gives me 1 mole of CO2. And that would get me 0.6007 divided by 2. 0.3004 moles of CO2. That again is pretty much the last piece of information that I need in the ideal gas law here to solve for what I'm looking for. Now, also before we go into the ideal gas law, we do have some conversions we got to do. So we have to add 273.15 for our temperature, and we also have to convert our pressure into atmospheres. Remember, it has to be in atmospheres, so we have to divide by 760 to get to atmospheres. So if we do both of those things, divide by 760 our pressure, that will get us 0.9803 atmospheres. We add our 273.15 to our temperature, like pretty much normal. That'll give us 296.15 Kelvin. Now we actually do have everybody in the right units. We once again can solve for volume, which would be nRT divided by P in this case. Again, dividing P to the other side to do that. Now putting that in here, our volume will equal our moles, our 0.3004. Actually, no, not RAM, so it's going to actually, I think, I'll go on this page here. So we'll do Our V is equal to nRT over P. So once again here, we'll take our moles, which was 0.3004. We'll do our R. We'll do our temperature there, which was 296.15 Kelvin. We're going to divide it all by our pressure that we had, which was 0.9803. And again here, the atmospheres will cancel, the Kelvin will cancel, the moles will cancel. It's going to leave us liters once again. And we will get 0.3004 times 0.08206 times 296.15 divided by 0.9803. It's going to give us something like 7.45 liters of CO2 would be produced in this case. So again, a reminder that always with a stoichiometry problem, whether it's a regular stoichiometry problem with grams of moles or even with gases, as we'll later see with volumes and molarity, you should always keep in mind you can still have a limiting reagent type situation occurring. Any questions on that there? Questions on gas stoichiometry here? Yeah. So the next thing we're going to talk about is Dalton's law of partial pressures, and sometimes people think sounds like a big name, so it's quite difficult. But it's sort of a straightforward sort of concept. So one of the ideas of something being an ideal gas is even if it's in a container with other gases, they will not interact with each other. So almost each gas you could think of, even though they're in the same container, are in there by themselves. So the idea here is if we had a container where the only gas molecule flying around is A, then the total pressure of this container basically is all from gas molecule A, as that's the only gas molecule that's basically flying around. Now, if we had a container where we had multiple gas molecules, like gas A, gas B, gas C, I could do the alphabet, so that's good. When we take the total pressure of this container, it's a result of the pressure of A plus the pressure of gas B plus the pressure of gas C, basically all added together. These are what are referred to as partial pressures because they are partially contributing to the overall pressure of that mixture. By the way, in the laboratory, the overall pressure of the mixture would be like we did in those experiments. It would be the barometer reading, the atmospheric pressure that you would get in that particular case. Now, how do we essentially figure out the partial pressures of everybody? Well, frankly, we can basically just use the ideal gas law. And as you can see here, we would use the ideal gas law, for example, for each gas separately. So however many gases there are in that mixture, so in this example here, A and B, we would just do the ideal gas law for gas A. We'll do the ideal gas law for gas B. Heck, if you had a third gas, you would do it for gas C. And when you would get all those pressures by just simply using the ideal gas law, all you have to do at the end is just add up all those partial pressures together, and that will give you your total pressure of mixture. Now, because all these gas molecules that are in this mixture are sitting in the same container, when you go into PV equals nRT and pretty much just solve for pressure, the volume for everybody will be the same because they're all in the same container, so they all have the same volume. That container is probably sitting in the same room, which means it all has the same temperature as well, because they're all basically, again, in the same container, in the same location, at the same temperature. So R is a constant. So really, when you go to sort of solve for partial pressures of different gases, really the only thing that's going to be different is the moles, is really the only thing that's going to be different in your calculation for each gas. So really, a lot of times, all you have to do is figure out how many moles of each of the gases you have. And then again, like I said, put it into the ideal gas law one at a time, get a pressure. That would be the partial pressure for that gas. And then to get the total pressure, you would just add them together. Again, this is still the ideal gas law, which means you need to make sure everybody's in the right units. So everybody needs to be in atmospheres for pressure. Again, volume here needs to be liters. Temperature needs to be Kelvin. Any questions on that there? All right, so why don't we try one here? Why don't you try one here? We take 5 grams of helium. We add it to 5 grams of neon. It's in a 2.5 liter container at 27 degrees Celsius. We're looking for the partial pressures of each gas and the total pressure. Helium there, 4.003. And was it neon, I think? Yep, neon. We'll go with 2018. All right, we're looking for 3 answers: partial pressure of helium, partial pressure of neon, and the total pressure. So give it a go. Okay, so let's take a look, see how you're doing. Again, here in this situation, we basically got a container where we have helium flying around. We got some neon flying around in the same container. Again, because we assume sort of ideal conditions, we're going to assume that they're really not going to interact with each other. So we could almost just frankly think of them as being in there by themselves. The volume for everybody will be the same in this case, 2.5 liters, as they're in the same container. Their temperature will also be the same since, again, they're in the same container. So that is 27 degrees Celsius, which obviously we know we're going to use a gas law here. So we might as well just convert it up front. So 27 plus our 273.15, that's going to give us 300.15 Kelvin. We obviously also always have R. So as we talked about before, in this situation, we have partial pressure situation. We are going to use PV equals nRT. And again, we're basically just going to use it individually for each of the gases that are present. So we really have temperature, we have volume, and we have R. So we do need to calculate the moles for each of the gases before we begin. So we might as well do that first. So we'll take our 5 grams of helium. We'll go to the periodic table and use the molar mass of 4.003 grams per mole of helium. The grams will cancel. Gonna get us 5 divided by 4.003. Probably helps if you hit the right numbers on a calculator. 1.249 moles of helium. We'll do the same thing for our neon. So we'll take our 5 grams of neon, also go to the periodic table, grab the molar mass there, 2018 grams per mole of neon. Again, the grams are going to cancel. So that will get us 5 divided by 2018, I hope. And that's going to get us 0.2478 moles of neon. Any questions so far? So we're ready really to calculate the pressure of each of these gases. And again, it's really, as I mentioned before, just an ideal gas law. We're going to divide volume to the other side. So P is equal to nRT divided by V. I'll do helium first. So what I want to use obviously here is the moles of helium. So 1.249. We'll use our R. We'll use our temperature, which we got 300.15 Kelvin, all divided by our volume, which is already in liters, so that was good to go. Liters will cancel, moles will cancel, Kelvin will cancel. Gonna leave atmospheres as the only unit left that does not cancel. That will give us 1.249 times 0.08206 times 300.15 divided by 2.5. Going to give us about a 12.3 atmospheres here. Atmospheres. And this is what is known as the partial pressure of helium. So that's basically helium's partial pressure. We'll do the same thing here to calculate the partial pressure of neon. It's, again, pretty much the same calculation. The only thing that's going to be different is obviously we want to use the moles of neon in this case. So 0.2478. All the other numbers will be the same because they're in the same container. All all divided by 2.50 liters. Again, everything's going to cancel except for atmospheres. And that will get us here for neon, 0.2478 times 0.8206 times 300.15 divided by 2.5, 2.44 atmospheres. And this would be the partial pressure of neon. First off, any questions on either of those calculations? So really, the most common way to calculate partial pressure is just to use the ideal gas law for each gas separately. Obviously, at this point, we want the total pressure, and our total pressure in this case would be the partial pressure of helium plus the partial pressure of neon. So really, all we have to do at this point is add them together. So we'll take each of those guys and give it a little add there. 14.7 in this case, atmospheres. The major contributor here to the pressure is which gas? It is helium, right? Helium is contributing 12.3 atmospheres versus neon's 2.44 atmospheres. The reason for that is right here. Helium is a much lighter gas, which means it's going to be flying around a lot faster. It'll have a faster velocity as it's moving around. And because it's lighter and moving around faster, because of that, it will cause more collisions and contribute more pressure than the slower moving, heavier neon gas, which will still be flying around, but not as fast and not causing as many collisions. Any questions on that there? We're not going to worry about that, I think. That's the one we just did. All right, so another obviously partial pressure situation that occurs has a lot to do with what we saw in the couple experiments that we did with gases, which is how you collect your gas. So this is the one we did the other day. You took your potassium chlorate, you heated this up, you had some oxygen gas being generated coming through your tube into your jar that had water in it, right? Gas bubbled in, water came out, hopefully into your sink. And you were left with this empty spot in your jar, or like in the tube that we did in the previous experiment as well. Again, in that empty sort of spot, in this particular case, that would be your oxygen gas. But again, as a result of how you collected this, because there's water and because there's sort of a reaction occurring, probably going to generate a little bit of heat, you will also get an additional gas, which you're really not interested, which is water vapor. And you end up basically with a mixture of two gases there. And that is a partial pressure situation where the total pressure would be the pressure of your gas plus the partial pressure of water. And as we talked about, that is what is known as the vapor pressure of water. That was that number that you looked up on a table. And because we're really not interested in this experiment or like the two that we did, either of those experiments, we were interested really in just the oxygen gas in the last one, and the first one we were interested in just the hydrogen gas. Water is really, in this case, just a byproduct of how you're collecting your gas. It's really not what you're interested in. So we oftentimes, much like in those experiments, has to do a correction calculation where the partial pressure of the gas we're actually interested in, which would be O2 in this example, would equal the total pressure, which is the atmospheric pressure, the barometer reading, minus the vapor pressure of water, which you can look up in the table. This is, as you saw in those experiments, sometimes referred to as the pressure of the dry gas, and it's referred to as the pressure of the dry gas because you're subtracting off water's contribution to the pressure, which you're not interested in. So it's like subtracting off the water and drying it out, if you will. So there's no sort of contribution for water. So this is another very common, as we saw in those two experiments, sort of correction he has to do to the pressure, and really a partial pressure situation in this case. Any questions on that there? And here is again a table where you can look up those values. It is based off of temperature, like you saw in that chart we had in lab. You look it up based on temperature, you can find the vapor pressure water you subtract off from the barometer reading. So why don't you take a moment here and do this one. A sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824 torr. Okay, so this is a situation just like we were just talking about. Basically, you collected this gas and you got the water vapor with it. How do you know in sort of textbook problems if this is sort of the situation? There's usually a couple of sentences that are sometimes used, and this is a very common sentence where it says, hey, it's saturated with water vapor. That's a really good hint that you need to do that calculation. Also, sometimes they'll say, hey, the gas was collected over water. So they mention something about water and how you collected the gas is usually a very key sort of phrase to tell you, hey, you got the total pressure is equal to the pressure of your gas plus the vapor pressure of water. So in this case, they did give us the total pressure, which is 753 torr. We're looking for the pressure of oxygen in this case. And they were nice enough, and they won't always do that in a problem. You might have to go to that table like we just saw on the previous page and look it up. But they did give you here the vapor pressure of water, which was 31.824 torr. So really, this is a really easy sort of partial pressure situation. You just got to subtract the two numbers, basically. So we're going to subtract those two numbers. And that's going to get us a 753 minus 31.824. Basically a 721 torr. Remember, though, that we do want it in atmospheres, so we could use our 760 number to convert. 760 torr is an atmosphere. So we'll take our 721 divided by 760, and we'll roll with a 0.949 atmospheres. Again, this would be our partial pressure of oxygen. This would be, again, sometimes referred to as the pressure of dry oxygen gas. Again, subtracting off that water's contribution, which we're really not interested in, as it's just a byproduct of how we collected the gas. Any questions on that one there? Okay. So I would say those are two very common sort of partial pressure problems that you come across. One is pretty easy. One's kind of like just a subtraction or addition type one. And one's more just go into the ideal gas law, basically. Any question on partial pressures? Okay. So we talked about here a lot of this stuff, but again, these are the main parts of the kinetic molecular theory of gases, which again, you should be familiar with. Gases, as we talked about, consist of tiny particles. They could be atoms or molecules. These particles are so small compared to the distances between them that the volume of the individual gas molecules is really not important. It's assumed to be basically zero. So this right here, as I mentioned a couple of times along the way, is one of the sort of reasons what we assume something to be a ideal gas is under sort of ideal conditions, the volume of the gas molecule itself is really not important. It's more important the volume of the container that they're flying around in. So again, as I mentioned, I think previously, if you look at a lot of problems, they will oftentimes talk about the volume of the container the gas is in rather than the volume of the gas itself. And that's one of the things that kind of makes something an ideal gas. The particles are in constant random motion, colliding with the walls of the container. It's these collisions that cause the pressure that we think about when we think about gases. Obviously, more collisions, more pressure, less number of collisions, less pressure. It's assumed that the gas molecules are not attracted or repelled to one another. Again, if you got multiple gas molecules in the same container, they're pretty much in an ideal situation not going to interact with each other. And that's really the second sort of part of this that makes something an ideal gas is, again, even though we got multiple gas molecules in there, They're pretty much going to ignore each other under ideal conditions. And that's what allows us what we just did there in that previous calculation or previous couple calculations. Even though we have a mixture of these gases, we essentially could do the ideal gas law for each gas by itself, like it's in there by itself. And the reason why it is important that they don't interact with each other is if you did have a gas molecule, for example, that was going to hit this wall, and let's just say that it was attracted to another gas molecule, it would actually slow this gas molecule down and it would have an effect on the overall pressure. Or if it was repelled by the other gas molecule, it would want to get away from the other gas molecule and perhaps have more collisions and stuff like that. So when we deal with most gases, we deal under ideal conditions. When you take 200A, you'll learn about real gases. Real gases are sometimes referred to as non-ideal gases. And in those type of situations where you have really high pressures and really small volumes, you actually do have to take into account both of those things. You have to take into account the volume of the actual gas molecule itself and the interaction between different gas molecules. And you'll get an equation that's based on the ideal gas law, but looks super scary because there's a lot more letters in it. And it's known as the van der Waals equation. And that is used for real gases. Good news is we don't do that in here, so that's a 200A. Wait for it, or 1A, or whatever they call that class here, you know, when you take that. The average kinetic energy of the gas particles are directly proportional to the temperature of gas. So as we talked about, as we increase the temperature, everybody's going to fly around faster typically. And as we lower the temperature, everybody's going to lose some energy and fly around a little bit slower. So just some of the relationships that we talked about there through the different gas laws and stuff that we saw. Again, higher temperatures, faster moving gas molecules. And obviously, we would expect more collisions to happen because they are moving around faster. And again, vice versa, if we lower that temperature, perhaps less collisions would occur. If we had a rigid container like we talked about with Guy-Lussac's law, because the volume will not adjust when we do see that rise in temperature, we definitely will see a rise in pressure because of the collisions. And when we lower the temperature, we'll see less collisions. In the Charles law relationship, we see that the way it's again able to maintain constant pressure is the volume adjust, as we talked about. So if we have a higher temperature, we expect a larger volume so that we can keep it at constant pressure. And if we have a lower temperature because they're flying around slower, we'll need to compress everybody together and we will see the volume basically decrease. Any questions on that there? All right, that wraps up the gas chapter. We're going to go off to the next one. Just give me a second here to pull it up, I think. Chapter 14, which is liquids and solids. So I believe this should be starting the next exam. So I think the one next week goes up to the gas chapter, if I'm not mistaken. So I think our exam's next week, if I'm not mistaken. So we will have liquids and solids here. We're going to talk about some forces that help liquids interact with each other. And we'll talk just a little bit about solids towards the end. Let's talk a little bit about water. And water, as we've talked about, is a colorless, tasteless sort of substance. It freezes at 0 degrees Celsius, and the normal boiling point of water is 100 degrees Celsius. It is liquid water between 0 and 100 degrees Celsius, and when water expands as it freezes, you're probably aware of that. And again, what happens is water is an unusual substance, as liquid water's density is 1 gram per milliliter, but actually solid water, which is ice, is actually less dense than liquid water. And that's because when water molecules come together, as we'll talk about, they actually create a pretty big volume or space between the different water molecules when they actually freeze. And you probably have seen this. Maybe you put like a soda can or something in the freezer and you forgot about it and you come back later and the bottom of the can is like bulging out. That's those water molecules freezing, trying to take up more volume, pushing out basically the bottom of your soda can and stuff like that. And the reason for that is because of the really strong interaction between water molecules that we'll talk about in this chapter. They just can't, in the solid phase, when they lose that much energy, get themselves that close to one another. So they actually are able to keep a pretty big distance. creates this big volume. If you think about, again, density, which is mass divided by volume, because it creates a lot of this open space volume between the water molecules, this number gets larger, which means the density gets smaller in this case, right? Small number divided by a large number gives you a small number, so you actually see the density come down. And then again, it's a very unusual sort of characteristic of a substance. Usually in their solid state, they're actually more dense than in their liquid state, but water is a little bit unusual. So as you can see there, the density of ice is about 0.917, again, less than liquid water. Also why when we put ice cubes in our drinks, right, they float to the top, right? And they're floating up on top because they're less dense than the major water part of your beverage. So this is a heating and cooling curve, and this is the normal sort of freezing point here. And this is at 100 degrees, our boiling point. And again, it's not until you actually get a little bit below 0 degrees, for example, that you actually have ice, which is the solid version, obviously, of water. And it's not until you get above 100 degrees that you actually have steam, which is the gas version of water. And obviously in the middle here, you have liquid. Now, when we talk about these guys changing from one sort of state to the next, and especially when we do a phase transition with something like water, there is a specific amount of energy that's required to do nothing more than actually just change a substance from, say, solid to liquid or liquid to solid. That is what is known as the heat of fusion. And the heat of fusion is the energy to do, like I said, nothing more than take a substance from solid to liquid or liquid back to solid, not changing the temperature. And that is because that happens at the normal melting point, freezing point. So if we take a look at this little thing, that is what is happening right here at this point on this graph. It's basically flatlined. You actually have both phases happening at the same time. You got a little bit, say, of liquid water at this point, a little bit of ice, some ice crystals kind of happening. And again, like I said, it's not until you get a little bit above 0 degrees that you fully transition to liquid water, or a little below 0 degrees that you fully transition to ice. But dead on 0, which is the normal freezing point, melting point, you will have both things happening. And that heat of fusion is the energy required to take ice at 0 degrees Celsius, for example, to liquid water at 0 degrees Celsius. So again, the temperature doesn't change when you do that. For water, it is about 6.02 kilojoules per mole. That is roughly about 335 joules per gram, give or take a joule. When we go from solid to liquid, that is an endothermic process. Energy has to be put into the ice cube to melt it. That is a positive number, right? When we talk about energy and positive numbers, that's endothermic. So it would be positive, for example, 335 joules per gram, or positive 6.02 kilojoules per mole. And if we wanted to take liquid water and freeze it, the energy has to be released from the liquid water, and that's going to allow everybody to slow down and basically come together in the solid phase. And that's an exothermic process. It would be negative 335 joules per gram, or negative 6.02 kilojoules per mole. So there is a certain amount of energy required to do nothing more than just take a substance, solid to liquid or liquid back to solid. Those numbers of 335 and 6.02 are specific for water. If we were talking about a different substance, it would have a different value for the heat of fusion. It would also, by the way, have a different value maybe for its melting point or freezing point temperature. It may not be 0 degrees Celsius. But again, these numbers are specific for water. Same thing here when we talk about our going from liquid to gas, our gas back to liquid. That is the heat of vaporization. And by the way, the heat of vaporization or the heat of fusion is oftentimes abbreviated as delta H of fusion. And this guy is oftentimes abbreviated delta H of vaporization. If you remember, delta H is the change in enthalpy that we talked about in that energy chapter way back when, yeah? Delta H is our change in enthalpy. So for water, like any other substance, there is a amount of energy that's required to take that substance from, say, 100 degrees liquid water to 100 degrees steam. Again, not changing the temperature, but to change the state of it. For water, that's 40.6 kilojoules per mole, or roughly 2,260 joules per gram. And that would be a positive 2260 heading in this direction, or a negative 2260 heading in this direction. And if we take a peek at the graph, that is what we're talking about right here. Again, it is flatline, which means the temperature is not changing. And we're taking it from, again, just one state to the next at the same temperature. That again occurs at the normal boiling point of a particular substance. So the normal boiling point, which is why it says 100 degrees there, which is the normal boiling point of water. Once again, the 40.6 kilojoules per mole, or 2260 joules per gram, is specific for water. And again, if you're doing some other substance, it will have a different value for the delta H of vaporization. So when we look at a heating or cooling curve like this one that we see here, and by the way, it's a heating curve going from solid to liquid to gas, right? So solid, liquid to gas, this is a heating curve. And it's a cooling curve as you go from gas to liquid to solid. When we go from, like I said, solid to liquid and do the transition, that is the heat of fusion that we would want to use. When we go from liquid to gas at the same temperature, that is the heat of vaporization. Now, there's some other parts of this curve which is kind of important as well. In this part here, as I go all the way through that green part, that is all the same phase. That is all ice, basically. It's all solid. And the temperature is changing. And if I start from here and go all the way up, that is all liquid all the way through there. And the temperature is changing. And if I go from here all the way up, that is all gas where the temperature is changing. Now, if I want to calculate the energy of a substance that is in the same phase, but the temperature changes, there is an equation to use for that, and perhaps you remember it in that energy chapter. That is our friend Q is equal to ms delta T, our specific heat equation. That is where you have a substance that's in the same state, but you change the temperature. So if you wanted the energy for any change that's in this part, where it's all gas, but the temperature change, or if you want the change in energy in this part where it's all liquid, but the temperature change, or here, you would actually use the specific heat equation to figure it out. And you could use the heat of fusion, heat of vaporization if you have any type of phase changes that occurs between them. Now, it's really important, the specific heat capacity, as you remember, for liquid water is that 4.184 number we saw way back when, or 1 calorie per gram per degree Celsius. That number is for liquid water, which is right in here. But you have to remember, though, that if you're doing something up here, or even down here, that is water in the gas state up on top, and that's water in the solid state on the bottom. It actually will have a different specific heat capacity. It's more like 2 joules per gram per degree Celsius for each of them. So it will change. So if you're not doing liquid water and you're doing something that is different, maybe going from solid all the way up to steam, you have to use the correct sort of specific heat equation. Any questions on that? There are specific value. So let's say we had an example like this and we wanted to figure out, for example, how much energy is required to change 75 grams of ice that is starting at minus 3.5 degrees Celsius and to take it all the way to steam, that is at 102. So essentially, we're starting way over here, and we want to end like way up here is basically where we're going. And if we do this, there are several steps along the way. The first step is we have we have ice that we need to take from ice at minus 3.5 degrees Celsius to basically ice at 0 degrees Celsius. So that is ice through that point, same state, but temperature changes. So we have to use the specific heat equation. So the first thing we would do is, like I said, ice at minus 3.5 degrees Celsius to ice at 0 degrees Celsius. That is a specific heat equation. Q is equal to ms delta T. Here we would have our mass, which is 75 grams. We would have our specific heat capacity. This is actually for ice, so this is not going to be that 4.18 number. You would look it up. You can never remember which one's which. So I'm going to go with, it's actually 2 joules per gram per degree Celsius. I'll just be off by a little bit if I am, but it's pretty close, I think. We have our final temperature of 0 degrees Celsius, and we have our initial temperature of minus 3.5 degrees Celsius, right? So if we put this into here, our Q will equal 75 grams. We'll use our specific heat capacity for ice. Our final temperature, which is 0, minus our initial temperature, negative 3.5 degrees Celsius. And that is going to get us here about 525 joules of energy. Again, our degrees Celsius will cancel, our grams will cancel. It's going to leave us joules at this point. This is positive, right? Because we're basically melting ice, right? So that makes sense. We ended up with a positive energy number here. That moves us now to, if we kind of follow on our curve here, the next step is we are sitting right here at ice at 0 degrees Celsius. We actually have to do a phase change and take it from ice at 0 degrees to liquid water at 0 degrees. So that would be the second step, which is our phase change. So we all has to go from ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. That is our delta H of fusion. Again, that is the energy, as we just talked about, that's required to change a substance from solid to liquid. Yes, sir. How do I get which one? You would have to look it up on a table. It would be on a specific heat capacity table. I'll be honest with you, I think it's 2, but it might be 203, one of them. The gas is 2. They're both basically about 2, but you would look it up kind of where you would find like that 4.184 number. Yeah. And probably in your book, it would be back in that chapter where we did energy, which I guess was not too far back. It was 10, I think, right? It's where we did specific heat. So here we would take our energy, our grams of our ice at this point. We would times it by the heat of fusion. I'm going to use the joule number. And again, for water, that is about 335 joules per gram. So that is what I'm going to use for my heat of fusion. I'm not going to use the mole one because, frankly, I want everything in joules. So I might as well just use the joule one. So 75 times 335 tells us it's going to require about 25,125 joules of energy just to do the phase change, just to take that much ice to at 0 degrees to liquid water at 0 degrees. So you basically got to put in there that much energy basically to melt it into liquid water at 0 degrees, basically. Any questions on that so far? The next thing that's going to happen is I am sitting here now at ice or liquid water at 0 degrees. I'm going to take it all the way up to basically liquid water at 100 degrees. So I'm going to go all the way up there. So the next step would be liquid water at 0 degrees to liquid water at 100 degrees Celsius. That again is the same phase, but we're changing the temperature. So Q will equal our MS delta T. So our Q here will still be the 75 grams. Here we will use the 4.184, which is the specific heat capacity for liquid water. Our final temperature is 100 degrees Celsius. Our initial was 0 degrees Celsius. And that will take us at 75 times 4.184 times 100. We will get 31380 joules. So that is the energy now to take us all the way up basically to the boiling point of liquid water at this point. And now we're basically sitting right here. And I think we will finish the rest next time. Any questions on that?